human hands let us solve a wide variety of tasks. For the past 60 years of robotics, hard tasks which humans accomplish with their pair of hands have required designing a custom robot for each task. As an alternative, people have spent many decades trying to use general-purpose robotic hardware, but with limited success due to their high degrees of freedom. Professionals trained a pair of neural networks to solve the Rubik's Cube with human-like robot hands. The neural networks are trained entirely in simulation, using the same reinforcement code as OpenAI Five paired with a new technique called Automatic Domain Randomization, ADR. By acting given algorithms, the system finds new combinations of Rubik's Cube rotation, and then the system uses these combinations to build the next Rubik's Cube. In addition, the system can handle situations that has never been before during training, such as being pushed by a teddy bear giraffe, which shows that reinforcement learning is not just a tool for visual tasks but can solve problems in physical worlds that require unprecedented dexterity. The team of researchers focus on the problems that are currently difficult for machines to master: perception and dexterous manipulation. We therefore train our neural networks to achieve the required face rotations and cube flips as generated by Casimba's algorithm. Domain randomization enables networks trained solely in simulation to transfer to a real robot. Solving a Rubik's Cube one-handed is a challenging task even for humans, and it takes children several years to gain the dexterity required to master it. The robot still hasn't perfected its technique though, as it solves Rubik's Cube only 60% of all the time and only 20% for maximally difficult scramble. Successfully training such a robotic hand to do complex manipulation tasks lays the foundation for general-purpose robots. The biggest challenge the developers faced was to create environments in simulation diverse enough to capture the physics of the real world. Factors like friction, elasticity, and dynamics are incredibly difficult to measure the model for objects as complex as Rubik's Cube for our robotic hands, and we found that domain randomization alone is not enough. Automatic domain randomization infinitely generates more complex environments in the simulation, which allows the system to be progressively trained to operate in more complex environments. Research measures the time to success per cube flip for our neural network under different perturbations such as resetting the network's memory, resetting the dynamics, or breaking a joint. We perform with experiments in simulation which allows us to average performance over 10,000 trials in a control setting. In the beginning, as a neural network successfully achieves more flips, each successive time to success decreases because the network learns to adapt. The strategy the network is employing doesn't work in the changed environment. The network then relearns about the new environment, and we again see to success decrease to the previous baseline. Yes, the system is still not perfect and cannot perform 100% of its tasks, but improving its performance is still a work in progress, because successful training of such a system will help in creating new robots for everyday life and helping people. Let us in the comments what do you think about the robots in general, and do you want to receive more helpful information about artificial intelligence? Subscribe to our channel and check out our Instagram and TikTok pages as well.